All right, cool. So yeah, kind of reviewing for like from last time, right? We really talked a whole lot about like neural networks. I think we kind of went a little bit over even, but that's kind of because we're squeezing in like 44 and 45 together. But I think they make sense. Otherwise, if we separate out 44 and 45, I felt like I kind of would just like say, all right, well, we can talk more about this, but not until tomorrow. So I think it made a lot of sense. But kind of as we kind of start into it, does anyone got any questions now that maybe you guys had some more time to digest or about neural networks in general? No, nothing too much. Cool. So today's going to be mostly focused about saying, okay, now we know the different parts of a neural network. We're going to kind of talk about, say, how do you avoid overfitting? What do we do to optimize our neural network and all that stuff? So I'm going to go share my screen. And I remember last time I had planned to show you guys implementation with Keras. So I'm just going to go over that today, right now. And you guys should all be able to see my screen right now. Looks pretty good. Okay, cool. So I gotta move my windows over since Zoom rearranges my windows when I share my screen. Okay, so this is where, note that most of this code is from like Keras.io. You can, I'm sure if you go search anywhere, like GitHub, anywhere, you can find plenty of examples. I encourage you all to like see what other people are doing, see ways people kind of implement this stuff. Because there's just so many different ways you can kind of like essentially put all these Lego pieces together and seeing how they work. And in general, like there are like, we'll talk about some optimization stuff and how sometimes neural networks can feel like black magic, where it's just like, I don't know what's happening, but if I make this change, suddenly it works fine. We'll talk about how to kind of like approach it a little more scientific. And also know that's like an ongoing area of research, is that people are constantly, trying to figure out the best way to implement these and figure out, what's going to work well. And we're going through different changes all the time. So yeah, but it'll be useful first to like see, let's implement this stuff out. Okay, so all right. And again, these are all found on the repo. So some useful inputs and stuff like this is just this, as far as to just our packages and everything like this. So note that I'm going to kind of cheat here a little bit. I don't think the curriculum talks about TensorFlow directly. I'm more familiar with TensorFlow. My computer's kind of set up this way. So I'm just importing Keras, which is what the curriculum talks about. So Keras is an API, right, that is going to allow us, instead of having, if you look in the curriculum, see all the mathematics and like seeing like how neural networks work, instead of implementing it from scratch, because unless you're doing something really novel or like, kind of practice things out, you usually aren't doing things from scratch. I will say is that like there are some benefits to doing things like a little get like down and dirty and like trying to figure out like, how to optimize this part. But for the most part, as a data scientist, that might not be your day in, day out. Most of it's like, hey, I want to do something that I know that works instead of worrying about the specific mathematics and like making this work. That's not to say that the mathematics aren't important, right? Because if you understand the mathematics, it's going to be a lot easier to understand when your neural network doesn't quite work out or your machine learning algorithm doesn't quite work out. But just know that TensorFlow, which is a package, actually, it's open source, but it's developed by Google. There's a kind of competing one, competing in the sense that like it's a different one. They're not, I don't know if they're necessarily competition, but a PyTorch, which was developed out of Facebook. They're both open source. But what's nice about TensorFlow, it does have Keras packaged within it. So if you are familiar with Keras, you can go ahead and use basically the API from TensorFlow using Keras. So just know that if you had your own thing, you could just probably just import Keras and it'll do the same exact stuff, or for the most part. Okay. Note that I put a random seed here. This is actually kind of an important part that I mentioned a couple times with my cohort, is that when you're doing a lot of these machine learning models, it's kind of a nice thing to have, like if you're doing anything with randomness, which a lot of times machine learning algorithms, including neural networks, have randomness built into it, that it's good to have like a consistent just what we call like the seed, so that way the randomness is consistent. So remember, computers aren't actually random, they're pseudo-random. Okay, they appear random, but this helps us basically debug some stuff. One thing to note is, you can choose your favorite number or whatever number you have near. You see a lot of notebooks have like 42, because like 42 meaning the meaning of life, stuff like this. But it doesn't really matter what the number is. The important part though is that you're not changing this seed just to see if you can get a better result. Because in that way, you're not really changing the algorithm. You're just trying to basically play the odds essentially. And that's where it's kind of like a nice thing to have, where like it's consistent and go through. Note that even with this part right here, there's still randomness built into like the other packages and stuff like this. Like for example, we'll talk about, how well, like when we do like stochastic gradient descent, this isn't going to directly affect it. So you still will get slightly different results, but this will make it a little less or a little more consistent. Okay. So, all right, I haven't even moved on past the first cell, but that's okay. And then of course, we're gonna import from Keras right here. I'm just importing it directly. So note that some people just put keras.models, keras.layers, but I'm gonna import this directly so I don't have to write it over and over again. So we have our models, layers, and optimizers, which we'll use in our actual code, okay? And note that here, because I'm using TensorFlow, it's just using the backend. This is partly so I can actually use a GPU as well. Okay, so now we have our inputs. Let's check out our data. Oh, question?
Yeah, this is probably a silly question, but can we just import models, layers, and optimizers in one row?
Yeah, you could. So if you did like this, you're saying, Lauren?
Yeah. Yeah, I was kind of confused why they split it out.
Oh yeah, it's
So,
just, I think it's just to be clear, but like typically you'll see it separated with commas and stuff like this. Um, I tend to do it this way because what will happen is that I'll have like a huge like chunk of imports and I look at those later on and I can't remember which one specifically, so I'll just do the same thing over. There's not really too much of a harm being done this way, but yeah, for conciseness, you could put layers and optimizers like all in commas like that. Cool. Good question, though. All right. So let's go into actually getting our data set. So I'm not going to go too much in this. We're using the Iris data set. Note that Iris is probably not the best example necessarily for neural networks and like what you'd actually be doing, because the Iris data set is less than 200 data points. But we've been, for at least for my cohort, we've been using Iris quite a lot. So hopefully we're kind of familiar with it and everything like that. There's also numerical features, so I don't have to like do anything too crazy with like making categorical one-hot encoding and all this stuff. At least nothing too major. So I'm just going to bring this data in here and then note that I get my train set right here. So note I have my X train and then my test data, right? So I'm doing that split. Note that typically you'll tend to do between like, I mean, for your test set could be up from as low as 2% up to as high as like 20%. In general, when we're doing neural networks, we're usually talking about big data. So if you have like 1,000,000 points, doing only 2% as your testing data usually is a pretty like decent size. Remember, the big thing we want for our neural network is as much data as possible. However, of course, we want to make sure that we can test it later on. But in this case, because our data set's really small, I'm just using 20%. So 80% will actually be used for, what's it called? Actually training your data, okay? And so I have my train, my test, and note that then in this case, I split it again into basically my validation set. So if you remember, validation set is really part of your training set, but your test set is kind of like your holdout. It's the thing that you kind of put off to the side. And you're like, I'm not going to touch this until I'm sure I'm done with training. And the idea there is that you don't want to start training against your testing set. Your testing is kind of like your final exam, right? You don't want to cheat on your final exam. You want to see how well like the machine learning model actually does. So that's where we're actually using our validation set. And our validation set is going to be our kind of like our little practice tests. So we train, basically study all of the training data, and then our validation set is going to be our little practice test where we say, okay, how well did you do? Oh, you didn't do that great. Let's try again, you know, and then do another validation. Okay, make sense to everyone? Cool. All right. So I'm just loading that data in here. Okay, and now actually to the creating the neural network. So in Keras, in the Keras API, we're going to build something called a sequential model. So sequential is basically what we've seen already. Basically, we're just feeding our inputs through the neural network, and it's going to push all the way through. So sequential, going, you know, layer 1, layer 2, layer 3, and all the way through. And later on, when we talk about things like LSTMs and recurrent neural networks, you won't have a sequential model. In this case, you can actually affect things in the past from what you've already trained, and so or already fed forward through. So just know there's a little difference here. But in this case, you'll probably use a sequential just for our basic model that we've seen already. Okay, so we're just building our model here. So note that this is very much like object-oriented. So it's sequential. It's going to build up this model. And this is pretty common terminology where we'll just have this model variable, and we'll just start adding things to this model. So in this case, we're actually going to go ahead and insert a dense layer. So a dense layer is what we've seen already. Basically, it's a bunch of neurons on that one layer. So we can actually do model.add. So we're basically going to like kind of build up our model. And this is our dense layer here. And we're going to put in 30 units. And so those 30 units are going to represent neurons, okay? And then our activation, so note that I put ReLU. We'll talk a little bit about activation functions and like what would be best, but in general, ReLU ReLU is generally thought of as like kind of like the good default. It's a good balance of, you know, quick optimization, but not necessarily ill-performing. We'll talk about this again, but don't use Sigmoid. Sigmoid is pretty much like, it's at this point, like it's been abandoned after like 20 years. It just doesn't perform very well. So that's where this part is. Note that I have to input the input dimension. So because I have to know how many inputs we're putting in, how many neurons are going into here. So this is an important aspect. What is nice though is that as we add more and more layers, I don't have to keep putting in like, you know, what the next dimension input dimension is, because basically we're adding it to the model. Keras API is smart enough to figure out like, oh, well, you're gonna feed it from, you know, 4 dimensions, so I need this many connections going forward. So the next one's gonna look like 30 connections. Like if I put this technically in here, input 30, that would be correct, but I wouldn't have to do that because it's figured it out itself. Okay, does that make sense? Okay, so now that I have this little hidden layer commented out, we're just gonna try a very simple one where basically I have just inputs, and then essentially our inputs are one hidden layer, which is our 30 units, right? And then we're gonna go straight over to our output, which in this case for the iris data, there's 3 different classes. So this output, like there, if I just quickly draw this over, see if I can draw this, yeah. So if you see something like we have our inputs for inputs like this. So these are different features that we have start off. And then I'm gonna have like 30 in this layer. I'll just draw this as like a big block, right? And then remember all of these neurons are all gonna connect to each of the other ones, right? So we're gonna have this really complicated looking thing. So each of those will have 30. And then from there, we're gonna have 3 outputs, 1, 2, 3, and those will all connect. I won't draw all those lines, obviously, but you guys get the point. Okay, those will connect to these guys. And what these 3 inputs, these neurons right here, just like inputs but outputs, these ones are going to represent saying, is it class 1, is it class 2, or is it class 3 with a certain percentage. So for example, if I have like, you know, at the end it says, okay, I put my inputs in here and it says 0.8, let's say 0.2, and then let's say 0.4. What this means is that it's most certain that it's going to be class 1, but it's not 100% certain. So the idea here is that it's going to say, okay, how certain are you for each one? And this is going to say, okay, that means we should classify as class 1 because class 1 is the highest value on this point. Okay, cool. All right, any questions? How are we feeling so far? Thumbs up? Yeah, thumbs down? All right, cool. So we built, so we're gonna go ahead and build our layer, or build our model. And note that I have some warnings here. You, for now, ignore this part. That's because I'm using a different kind of thing, using TensorFlow in this case, but that's okay, we'll just ignore that. So I built my model, right? I have nothing other than just build the structure. It doesn't even know what the inputs are, or it hasn't got any data yet. So what we're gonna do now is we're gonna compile it. So in this case, this is kind of like building like the extra hyperparameters. So you'll see here my loss, my optimizer, and metrics. This is kind of like first part right here. It's just saying, here's what the drawing looks like. This is the structure. These are the different hyperparameters now. I'll tune with that structure. So in this case, I'm using a certain kind of loss. In this case, I'm using categorical cross entropy because we're doing categorical. It's going to be class 1, class 2, class 3. If you're doing regression, you would have a different kind of loss. Okay, there's a whole bunch of different losses you can see here. Okay, so you can search for Keras style losses. Optimizer, we'll talk about optimizers in the future, but one of the things is basically to help speed up the training. And so you can see here are some other hyperparameters, our learning rate, our momentum, which we'll talk about. We'll also have this parameter here. We won't talk too much about this, but in general, you'd want to set this to true. I think that's actually the default for SGD stands for stochastic gradient descent. And you can see here, oh, that's not the default. I did change it over to false. You can look at the full documentation. There's so much more you can kind of go into, but just to get the basics. And then this last part, this metrics here, this is just a kind of like some extra information that we can see as the model's being trained. So this doesn't directly affect anything that the model's going to do other than just kind of output as it gets trained. Okay. So I'm going to do model.compile, and this basically says, all right, we're going to have the structure already. We're going to compile it with these kind of hyperparameters, and now it's like, all right, it's like set and ready to be trained. Okay. So what's nice is sometimes it's nice to just kind of check out, it's like, hey, what's the model look like? So you can do this model.summary. And this will actually print out, what the model looks like. You can see, for example, different layers. You can actually name these layers as well. In this case, I named it just the default dense 1, dense 2. You can see what type of layer. So we'll talk about different things you can kind of put in there as like different layers and stuff like this. And then you can also see what's nice is how many parameters there are. So this actually counts in saying how many different, well, in this case, anyone got to guess what does parameter mean in this context? What are we counting? When did we say there's 150?
Weight.
Yeah, weights, that's right. Yeah, so there's 150 weights. And you notice, if you remember back, we had 4 inputs, right? So 4 inputs, there's 30 nodes over here. Why is it coming out as 150? Why isn't it coming out as 120? You got to guess. So there's a little secret one. It's our bias. It's our 5th input. And so our bias is always put in there basically to figure it out. So we have our 5 different inputs. One of them is including the bias, all connecting over to 3 different nodes, 5 times 30, 150. Okay. So what's nice here too, it gives us a little output of saying, how many total parameters there are. Note that trainable parameters, when we talk about transfer learning next week, this will actually be a little bit, could be a little bit different because maybe you free some of those different weights and you don't change them. Say, don't change this weight no matter what. But here we're just training all of them. We're going to adjust all the weights as we go through it. Okay. So note that this parameters can get literally up into the millions depending how big your network is. So another nice thing to see is like your actual layers. So you'll notice here, this is kind of like object-oriented programming notation, right? So if you guys remember back from OOP, this is actually showing us where in memory the computer lives. So basically you can notice that this right here, these are called like its memory address. And you can actually see they're slightly different. So we have F60 and this is 6A0. So that's because they're 2 different layers. And you can actually get that specific layer by the name, for example. You can see I'm just going to get it by name, and we can actually take that one and you'll see it's the same address as this guy. Okay. So this might be useful, for example, like kind of looking at it later on, like when you do transfer learning, you can actually get the different weights. You can load the weights into there. So for example, if someone else made the same structure, but you're like, hey, I like how they did their weights. Let me start off at that point. You can actually load the weights in here, or you can get the specific weights. Here you can see I did model.layers and getting the first one, which should be the same exact thing as this. And then I can actually get the weights. In this case, because the first layer is going to be weights and biases, we can actually see what they're initialized as. And you can see here is that here's all the little numbers, right? So what's kind of cool about this, I can say like, where did all these numbers come from? This is because we actually initialized it by default randomly. It turns out initializing your weights randomly is a much more preferred way to initialize it over like just putting all zeros, because zeros basically you might not adjust your weight strong enough. So this allows it to basically start off just randomly through here. Sometimes you might actually load up your weights with an initial parameter or set of weights, and that will basically kind of kick off your training. Okay. So anyway, this was a little bit of like looking at the model before we actually train it. All right, so we got all our different model structure. Anyone got any questions about what this looks like or anything? I kind of ran my code on here. Looking pretty good. All right, so last part is like, okay, let's go ahead and, oops, where am I? Oh, training my model. So we're gonna go ahead and train the model. So now we're actually, okay, we crack our fingers and say, all right, let's go ahead and feed this beast, our data. So we have our X train, our Y train on this model.fit. Note that I'm gonna save this history. This is pretty common practice where we do like history equals model.fit. That way we can check out later on like how the model does. We have X train, Y train, epochs or epochs, depending how you pronounce it. This is just how many times we're going to iterate through this process. Batch size, which we'll talk about, basically instead of feeding it all of the data, which I think this actually won't work well, so I'm actually going to get rid of this. No, I'll keep it there. This batch size is basically how many points you're feeding it through. But because I think it's iris data, I think this will actually do the whole data set because it's relatively small. But instead of doing all of it at once, you can instead feed it little by little. Okay. And then we have a validation data set, X valid and Y valid. Note that if I didn't have this right here, you could potentially do a validation split and to say how much of your original data you should save for validation. And this will basically randomly pick it. So note that instead of doing this, you could have potentially done validation split equals like 20%. Okay. So you go ahead and run this, and this is the one that will take a while. So you can see here, I only did 50 epochs, and it's a relatively small model. So you can see it only took like about 744 milliseconds, so less than a second. But you can see here going through, how well the accuracy, the validation loss, validation accuracy gets a little cut off right here. But you can kind of see how your model's performing going forward. Okay, cool. All right, that was pretty pretty quick, unexciting, right? You could also, if you wanted to, I just put this little thing, you could potentially just train on a specific batch. So you can actually do this manually, so like train this one batch and then like give it another batch, and then give another batch. So kind of like instead of doing this like epochs equals 50, you could do like a for loop and train specific batches. This is a little more on the research side. Generally, you'd probably just run it like this. Okay. So now we can actually see if our weights have changed. And if we look at this now, we can actually see that our weights and biases have changed. So this is actually saying the model says, all right, after 50 epochs, we got this validation or this accuracy, this error was minimized to a certain point with these weights and these biases. Like, all right, cool. So you can actually save these later on and actually load them in later on and all that stuff. So this basically is telling us how the model performs or how the model makes its decisions. Okay, so now we can check out evaluation. So note that I'm just going to go use pandas here because I'm familiar with pandas, and I'm just going to get those specific columns from the history. So note that I saved history equals model.fit. I can do history.history. So this is going to give us basically a dictionary of different, what's it called, of the accuracy, validation accuracy, I think loss and validation loss. So we can actually see here is the plot of how well it performs. So we had our validation data, so we can actually see the accuracy kind of goes up and up. And you can see here on this training part, this is what the the accuracy in blue is our training. You can see it kind of has these punctuated parts, right? It kind of like does decently and then goes up. So it might be finding something in general. And then you, this validation accuracy, you can see it's lower, which is kind of what we'd expect, right? Note that if you're doing for a small number of epochs, this is actually should be changed up by one like epoch because we don't do the accuracy until after we train it. So it might sometimes look like validation is actually higher, like a better accuracy or lower error than validation or than the actual training, this guy right here. And that's just because of just probably it's being pushed over one by on the graph. So just kind of be aware of that if you see that sometimes. And then you can see here in this case, usually we don't talk about accuracy directly, we might talk about more about loss. And you can see in this case, is that the validation or the loss rate here in the training gets smaller and smaller and smaller. We can see here for the validation loss getting smaller and smaller and smaller, which is what we want. Ideally, we want these as close as possible, and we want to have it not, what's it called? Like you don't want it to just flatten out, right? Because if it flattens out, it means it's reached its peak. Or if you see it start going up, that means it's overfitting. Okay, cool. Understandable so far? Yeah. All right, so a couple other evaluation stuff you can start seeing like, okay, let me go ahead and evaluate on a specific one. So you can see here like X test and Y test, which we kind of held out. Let's pretend we did a whole bunch of modeling stuff like this and we see how well it performs. And basically we'll see, okay, how well it actually did. And we can see here, this is its loss right here, 0.658. And we can see our accuracy is about 0.8, which is actually pretty close to like what we had before here. So our test set actually seems to match pretty well with our validation, or not our validation, but our actual like results here. Okay. And we can actually go ahead and make predictions. So remember we have either, I said class 1, but it should be class 0, class 1, and class 2. We can actually say what predictions each one. So what's kind of cool is that this right here is telling us what it predicts each one. So this is going to represent in this column class 0, this is going to represent class 1, class 2, and these are each data points. So for the data points of whatever features of that first one is, it's saying, hey, we have a prediction of about 82% we predicted. We have an 82%, like you can think of it like, there's an 82% confidence in a way, like saying this is going to be class 0. And it's like, okay, it might be class 1, 10% sure. And you can see here basically these parts. You can see certain ones, like these ones are pretty certain, it's class 0, but this one right here, you can see it's not sure. Like, sure, it's class 2 technically, but you can see it's not super confident. It's about like, it's more or less equal. So this is a great way to kind of just check out what's going on. But to kind of see things, this will always be true. Like we won't ever get 100%, and most likely. So we can actually take this guy and say, okay, let's go ahead and see the most one, right? So we want a list of like zeros, 1, or 2, right? And we can say, go ahead and take the biggest one. So this is what np.argmax is, the argument maximum. So we're going to do this, and we can see predictions now, and we can see for these data points right here, it's at 0, 0, and 2, and you can kind of see from the very beginning, this would be 0 because this is the most, this is 0, and this is going to be 2 because this is the most. Okay. So that's a kind of a quick way to just see what the classes are. You can also then see like exactly like, percentage, like saying how well your accuracy is, and which 0.8, which matches with what we had up here. Okay, cool. Sound all pretty good? Okay, cool. So let's kind of go back a little bit real quick and let's just modify this a little bit. So I'm gonna go ahead and make this guy, we're gonna add a extra hidden layer. So now that I'm gonna put 16 layers, units in here. So now you have 2 hidden layers, 30, 16. I run this guy. We'll see the model summary now. Oops, I ran this twice. So, okay, we're gonna add a lot of layers in here. Note that I put this together. So if I ran this guy and then did this, you'll see now I'll have just those 3 parts. But if I ran this twice, like I ran it again, and then compile, you'll now see that I did it twice. So be very careful because your notebook lets you run things multiple times, right? But I'm actually not going to do this because this softmax is going to mess things up in the middle. So I'm going to actually just run it with just 2 hidden networks, or 2 hidden layers. All right. And then let's go ahead and train this guy. And note that this took about 744 milliseconds. Let's go for, yeah, we'll try it for 500. So maybe we can see a little bit better. And I'm going to get rid of this batch size because I don't think we need this anyway. Okay, so there it goes. And you can see it's still going, executing. In fact, if you scroll to the bottom here, oh, it already finished. But basically, if this was a little bit slower, you would actually see this arrow kind of run across here. And you see it took about 5 seconds. Okay, so now we go ahead. I'm going to skip over that part and actually see how well did the accuracy versus validation accuracy. And you can see in this case, our accuracy is getting up to 100% after 200 epochs. Wow, that's awesome. But you can see the validation here kind of slowing down a little bit, right? And so if we run this guy here, we can see the loss, and you can see here we're definitely getting to this point where it might be starting to reach essentially its point. There might still be room for improvement since this thing hasn't really changed in its size between the two, but we probably would need to do some extra parts because this training accuracy, it's not really training after this point at this over here. Okay, so let's see evaluation. In this case, we got 83%, ooh, a little bit better than before. And we can see our predictions, our argument max. So I'm actually going to go ahead and copy this so you can see a little bit of different comparison. So you can see in this case, it actually decided 1 instead of 2 before. And you can see it's a little more confident in this case. Well, a lot more confident. Before it was like nearly equal. So yeah, so you can give it more time and stuff like this. So you can see this different iteration. Okay, make sense to everyone? Yeah, cool. And yeah, 83%. All right, so what's one thing, I don't think the curriculum necessarily says this, but I think it's kind of an important part because like, hey, you run your model, you don't want to have to rerun it again, especially if you ran it over an hour, 2 hours, 4 hours, and you like close your notebook and you're like, oh wait, what were the weights? I never checked it. You can actually save your model. So this will actually save it into a file called an H5 file right here. And this will actually take your model, this is just the name of it, and this will save this model into your directory. So if I go back to where I ran this, you can see now my model.h5. Okay, so it's nice that this is a way to package it up, and that way you can save it for later. You can then maybe send it off to someone else. They can use it in their application, stuff like this. And so if you were to have a model that someone else built, or maybe you built, you can actually load that model directly here. So you can see right now, if I just go ahead and put in loaded model, oh, I don't have it. It'll show me an error, right? It's like, oh, there's nothing in there. But if I do this guy, this is going to load my model that I had just built. And I can actually do, let's see something. And you can see, here's my model. In fact, you can now get oops. Yeah. Oh, wait, I need to get the, oh no, that is everything. So you can see all the weights are here too. So you can actually pull this up directly. Okay, note this is going to be the weights of the whole model. So pretty long. Because it was like was it a few hundred parameters? Something like that. Oh, yeah, about 700 parameters. So there's 700 numbers in this guy. Here. Okay. Any questions on that kind of implementation, what that looks like?